All right, in this lesson, we will be looking at the factor theorem. So we're going to be looking at how you can make use of the remainder theorem to actually be able to factor any kind of polynomial. Okay, so let's just go over some techniques before we get to the factor theorem. So one way you could factor polynomials that are not just quadratic is to use grouping. So grouping can work with large polynomials. The thing is, the polynomial just needs to be set up nicely. So with grouping, usually what we do with grouping is we common factor, let's say in pairs. So in this case, I'm going to look at this x cubed plus 2x squared and minus 16x minus 32. And I'm going to look at those two pairs, and I'm just going to common factor what I can. So in the first pair, I can common factor out an x squared, and you're left with x plus 2. And then the second one, I'm going to take out a 16, and I'm also going to take out the negative, so minus 16. And then you're left with x and a plus 2. And when grouping works, what you'll have is the leftover parts after you common factor are going to match. And so actually what you're doing is, in a sense, another common factor. So x squared minus 16 and x plus 2. You've basically common factored out that x plus 2 from both x squared and 16. Okay, and you could actually factor this a little bit more. X squared minus 16 could turn into x plus 4, x minus 4, x plus 2. And there we've factored that cubic polynomial. So yeah, grouping works. The thing is, how do you make sure, or how do you know grouping can work? Because it's definitely like a quick and efficient method. To know if grouping works, all you need to do is you just need to check out basically the coefficients on the first and the last. And so if we have a general polynomial, we could call that a. So yeah, the first and the last, 1 and 32, just multiply them together and just see, does that multiply to the same thing as the insides? And well, what do the insides multiply to? In this case, we'll do it in purple. 2 and negative 16. Oh, and really that should be negative 32. 2 and negative 16. And that's going to equal each other. Negative 32 equals negative 32. So I'll say outsides equal to the insides. Or if you're looking at it in general, like the coefficient, if you're thinking A, B, C, D, A, B, C, D, then A times D is equal to B, C. If that is true, then grouping will work. So it's very specific. So it's nice when it works, but we can't rely upon it. So we need to figure out a more general method, and that's going to be what we call the factor theorem. So let's take a look at the factor theorem. And I guess I've repeated this down here. So the factor theorem is essentially very closely tied to the remainder theorem. It's just actually really just a specific case of the remainder theorem. What it says is, if you have a factor of a polynomial, if you know something is a factor, let's say x minus b or whatever it may be, then using remainder theorem, its remainder must be equal to 0. Or, well, the remainder theorem says plug in the root into the function or into the polynomial, and it will equal 0. And this term, if and only if, that means this goes in both directions. So we go to the right and also to the left. So what that also means is, if I find something that has remainder 0, that number that I've plugged in will also form a factor. that factor could be just a single number, or if you have a fraction that you're plugging in, like in part 2 of this statement of the factor theorem, then it just means the factor is written as ax minus b, because if you were to solve ax minus b, set that equal to 0, find the root, well then that would solve to b over a. So that's what's happening there. And that's the direction we're really going to focus in on to actually be able to factor. So let's just get a hang of factor theorem. So is x minus 2 a factor of that polynomial? So what we need to do is check, we'll call this polynomial p of x, check if p of 2 equals 0. So let's just check that. P of 2 is going to be equal to 2 cubed minus 7 times 2 squared plus 9 times 2 plus 2. And when you substitute that in, what you will see is that you will get, well, what do you know? 0 in this case. So, therefore, x minus 2 is a factor. Okay. And that's what we're going to actually do to be able to factor, is we're going to search for numbers that make our polynomial equal to 0, and then we're going to use those numbers to form the factors. Okay, and that's going to be this method that we're going to go through here. So we're going to factor fully that x cubed plus 8x squared plus 19x plus 12. And so what we're going to do, and this is going to be called the integral zero theorem, essentially part of the factor theorem, is that the potential numbers that could make this entire polynomial 0 that we need to check are going to be the factors of the final term, of the constant term. And that's going to be the key thing. That's true if we're looking at something which has no lead coefficient. We'll see what happens if there is a lead coefficient, but in this case, we just need to look at the constant term. So the possible values of b of our factor must be factors of 12 in this case. And what are factors of 12? When I'm saying factors, I'm talking about numbers that multiply to 12. So it could be 1, 2, 3, 4, 6, 12. All of those, if you divide 12 by those numbers, it cleanly divides. So we're not looking for decimal values in this case. Just nice numbers that multiply together to give you 12. Not only that, you could actually have all of these be negative as well. So we do need to take into account negatives. So what do we do here? Well, we just have to go through and check. So it sometimes takes a little bit of work, but sometimes you can kind of go through it a little bit smartly. So you can notice maybe like, oh, these numbers aren't working, let's skip to negatives. But yeah, you just have to check all the possible factors until you get one that's equal to 0. Okay, so let's just start with 1. So p of 1, and that would be associated with the factor x minus 1. So that'll be 1 cubed plus 8 times 1 squared plus 19 times 1. So have your calculators at the ready. And, well, 1 plus 8 plus 19 plus 12 is 31. I want to say around 40. But essentially, the main important thing is it's not equal to 0. So that's not going to work for our purposes. Okay, on to the next factor, p of 2. We have 2 cubed plus 8 times 2 squared plus 19 times 2 plus 12. Okay, in this case, I have some positive, adding a number, we're adding another number, we're adding another number. We're just adding a whole bunch of numbers together. There's no possible way that can get down to 0. So that's definitely not going to be 0. And in fact, if you plug in any positive number, you're never going to be able to get to 0. So we need to actually check our negatives. That way we can have some subtraction going on, which will maybe cancel things out. So let's check negative 1. So we will have negative 1 cubed, which is negative 1, 8 times negative 1 squared is 8. 19 times negative 1 is just, well, negative 19 plus 12. Now add these up. 8 and 12 give you 20, minus 1 minus 19 cancels out. You get 0. So there we have it. We've got something that gave us a 0, and then, well, what was it? It was negative 1. So therefore, x plus 1, because when you solve for x plus 1, the root would be negative 1. X plus 1 is a factor. Okay, so that's kind of the first key step to factoring polynomials. Find the factor by finding something that gets you equal to 0. The next step, well, what have we been doing in previous lessons? Is we've been dividing. So all we need to do is take our given function, or polynomial, x cubed plus 8x squared plus 19x plus 12, and now we just need to divide it by x plus 1. That is kind of the second key step. And what we're going to see is that factoring will just become a nice repetitive algorithmic process until we get things fully factored. Okay, so let's do this division. So you could do long division or synthetic division. I'm going to go with synthetic division, but if you choose to do long division, that's totally fine. So I'm going to write down the coefficients, 1, 8, 19, and 12. I'm going to write down x plus 1. The root would be negative 1, the thing that we plugged in. That got us 0 is negative 1, so that goes on the outside. And then we start our long division, or our synthetic division. So we drop down the first number. That becomes 1. And then we multiply negative 1 and 1, gives us negative 1. The second number is is positive 7. And we continue. So 7 times negative 1 is negative 7. 19 minus 7, I think, is 12. And then negative 1 times 12 is negative 12. 12 minus 12 is 0. Okay, and this is going to be the important part, and it's a good way just to check your work. We just found out that x plus 1 is a factor. We just showed that p of negative 1 is 0. That means we just found our remainder. So when you're doing your division, you should always get 0 as your remainder. Since we confirmed that above. Using remainder theorem. Okay, so now let's take a look at what we have. So the division process here, we have 1, 7, 12. Remember, that's like basically a degree down. So that would be, instead of starting at x cubed, we start at x squared plus 7x plus 12. So our polynomial is going to now be, I'm just going to label things p of x, just so we don't have to rewrite it all the time. P of x equals, let's do that at the very start. I actually should have labeled that before because I've just been calling it that. So p of x is equal to, and it's going to be x plus 1, the thing that we divided by, times x squared plus 7x plus 12. This is essentially the multiplication statement that we did when we were dividing and showing our final answers. Normally with the multiplication statement, you'd have the quotient, which is the answer, the divisor, which is the x plus 1, and you'd add on the remainder. But the remainder is 0, so you don't need to have that there. And that's why division works, because when we have remainder 0, all we have left is that multiplication, which is just factoring then. Okay, so now we're not quite fully done yet. X squared plus 7x plus 12 could still be factored further, but at this stage, since it's a quadratic, you can just use your methods from factoring quadratics. What multiplies to 12 adds to 7? I think that's going to be 3 and 4. So we get that. So this is now factored. So that's going to be the key. And that's going to be the repetitive process is essentially finding that factor by plugging in numbers until you get it, divide. And just do that over and over again whenever you're factoring. Okay, but just keep in mind that process, it can be a long one, so always check if you can factor by grouping. It's efficient, but again, very specific. Or common factor. Common factoring, like maybe there's something you can just pull out of the entire thing, can be done as well too, and that can be easier. But if those don't work, then just go through the process that we just went through. Okay, so let's look at this one. Can you common factor? No. Can you factor by grouping? Not really. So let's go through the full factoring process for this. Okay, so what we need to do is we have no lead coefficient. We just have the number at the end, the constant. Check its factors. So 6 has factors 1, 2, 3, and 6. We need to check both positive and negative. So just plug in numbers until eventually you get it. P of 1 is just going to be 1 plus 5 plus 5 minus 5 minus 6. Well, that's 11 minus 11 is actually 0. So there we go. We actually got it quite quickly there. But again, if you don't get it the first time, just keep trying different numbers until eventually you get one that works. So therefore, x minus 1 is a factor. Okay, so step 2, we found our factor. Now we need to divide by this factor. So we're going to do x to the 4th plus 5x cubed plus 5x squared minus 5x minus 6 divided by x minus 1. Okay. So we can do long division or synthetic division. Again, I'll choose to do synthetic division just to keep things a little bit more efficient. But again, feel free to use long division if that's what you're more comfortable with. Okay, so for synthetic division, write in your coefficients. And then bring down that first number. That's going to be 1. Multiply 1 and 1, that gives us 5. Add those together, that gives us 6. 1 times 6 is 6. Actually, in this case, it works out very simply because it's just 1 in the front. And 1 times anything is itself. 5 plus 6 is 11. So then we get 11 up here. Negative 5 minus 11, or negative 5 plus 11, that's going to be just 6. And then 6 and negative 6, as expected, should give us 0 because we know already that's the remainder. Okay, so now we have 4 terms there. That's basically the next degree down. So instead of x to the 4, we now have x cubed plus 6x squared plus 11x plus 6. Okay, so p of x as a whole is going to be that factor that we just divided by times the quotient, which we just found out. X cubed plus 6x squared plus 11x plus 6. And since we have remainder 0, there's nothing there because this is a part of factoring. Okay, so now we're good with the first part. We've factored that. We want to keep factoring the next part in the brackets. How do we keep factoring? Well, guess what? It's not a quadratic, so we can't use our techniques from quadratics. We have to keep using whatever techniques we have to keep factoring. That might mean using the factor theorem all over again. And in this case, it is going to mean that. You could double check real quick. Can you do this by grouping? Well, if you look at the outsides, you have 6 and a 1, and the inside 6 and 11, they don't multiply to the same thing. So you do need to keep factoring by using the factor theorem. Again. Okay, so what I'm going to do just to make things a little bit, I guess, mathematically sound, is I'm just going to label the part inside the brackets f of x, just so we're not using the same letter, because otherwise, when we start plugging in numbers, well, what are we plugging it into? We're plugging it just into the part inside the brackets, not the entire thing. So let us test out numbers. We know that we need to test out factors of the constant which are just going to be, well, for 6, the same ones we checked out before. 1, 2, 3, and 6. And so just start testing out numbers. If you check f of 1, well, it's all pluses actually. So 1 plus 6 plus 11 plus 6, that's not going to work. So let's check some negative numbers out. I'm going to check negative 1. Negative 1 plus 6 minus 11 plus 6. That actually does end up equaling 0. So therefore, x plus 1 is a factor. Okay. Sometimes it might take more work. In this case, our small numbers are working out. You might have to check 2s or 3s or things like that in the future. Okay, we found our factor. So what do? Divide like we did. But this time we're just dividing the x cubed part. So x cubed plus 6x squared plus 11x plus 6. Divide that by, well, what do we just find the factor? X plus 1. I'll do synthetic division again. So we have the negative 1 on the outside. We have our coefficients 1, 6, 11, 6. And bring down the 1, multiply together. Add up that column, that's 5. Multiply together, negative 1 and 5 is negative 5. 11 and negative 5 is 6. Multiplied by negative 1 is negative 6. That gives you 0. And that part is going to be x squared plus 5x plus 6. Okay. So now we're getting pretty close to having this fully factored. So p of x is going to be the original thing we had, x minus 1. And our second factor, we just found x plus 1. And now the leftover part is x squared plus 5x plus 6. And well, now we've got it down to a quadratic. A quadratic we can factor using just our usual old techniques. That's why we still need to know those old techniques of factoring, because they'll keep coming back. And two numbers that multiply to 6 add to 5. Well, that's going to be 2 and 3. And there we go. X minus 1, x plus 2, x plus 1, x plus 2, x plus 3. That is the final factored form. So yeah, these kinds of questions, they can sometimes take a little bit of time just because you may have multiple factors to find, multiple divisions as a result to perform. But again, it's an algorithm. So take the time to practice it, and the more you practice it, the better you'll get at this kind of thing. Okay. The rational zero theorem. Okay, so it's a big name, but really it's just an extension of the factor theorem. In those previous examples, what you'll have seen is we never had anything in front of the lead term. So what happens if we do have a lead coefficient? Well, what that means is one of our factors, if the overall polynomial has a lead coefficient, one of the factors themselves might have something. I'm just writing out an example like this, 5x plus 2. One of our factors could have a lead coefficient as well too. And actually, one of them will have to for us to eventually get one. Could be one, it could be all. We don't know when we're first building this. So essentially one or all factors may have a lead coefficient. May have a lead coefficient if the polynomial does. Okay, so we just have to adjust our factor theorem, because our factor theorem up above, we were just checking for basically factors like x plus or minus some number. But now we need to include that lead coefficient, which means we need to check for fractional factors. That's what this is saying. And how do we get that fractional factor? Well, essentially, to get the fractional factor, we look not only at the factors of the constant at the end, but we also have to look at the lead coefficient. And how we're actually going to construct that is, it's not just the two numbers we're looking at, but what we're going to check is we're going to basically create a fraction out of the 2. So the 4, that's going to create our numerator. And then what do we divide by? Well, the denominator is going to come from the lead coefficient. And so that's going to be, in this case, well, 5 just has 1 and 5. And I'm not going to do like plus or minus on the bottom, because as long as we have it in the numerator, well, that will make the whole fraction positive or negative. So that will handle all of that. And yeah, the reason why the lead coefficient is coming from is going into the denominator is if we think about solving for the root, like in 5x plus 2, well, what happens if you solve for 5x plus 2, set that equal to 0? Well, that 5, the lead coefficient, when you solve it, goes into the denominator. So that's why it's happening here as well too. Okay. So the process is going to still be actually the exact same. So I'll call this polynomial p of x. And so we still check all these possible numbers. We just need to possibly check fractions as well too. So you could, in theory, check something like p of 1 over 5. P of 2 over 5. P of 4 over 5. Oh, should write that out correctly. And their associated negatives, so on and so forth. But, I mean, you don't have to start with that. You can still start with the simple cases. So to start simple, what I mean is just, well, check p of 1. Because that's just the fraction 1 over 1. 1 over 1 is just 1. So start with just your regular integers, and then move on to the fractions if you can't get anything with the regular integers. So really, it's just kind of a last final check. So p of 1 will just be 5 plus 3 minus 12 plus 4. And guess what? That's 0. So just like that, we actually already found it. So x minus 1 is a factor. So just because we have something with a lead coefficient doesn't mean your only factors are going to be fractions, or only going to come from fractions. You can still have just regular factors too. So let's do a little bit of synthetic division. So our form, or our function polynomial is 5, 3, negative 12, and 4. And just go through and divide using the synthetic division. So the 5 drops down. 5 and 1 gives you 5. 3 plus 5 is 8. 1 times 8 is 8. Negative 12 and 8 give you negative 4. And so negative 4 will go to the right and cancel out with positive 4. Remainder 0. That's good. And the remaining parts, those give you 5x squared plus 8x minus 4. Okay, so now what that tells us is the polynomial is going to be equal to x minus 1, what we factored out, essentially. And we're left with 5x squared plus 8x minus 4. That's a quadratic. We can factor that as we would quadratics. It's got a lead coefficient, so we got to be a little bit more careful with that. So what adds to 8 and multiplies to, now the outsides are negative 4 and 5, 20. And that would be, oh, I should say negative 20. That would be 10 and negative 2. So yeah, since it's a complex trinomial, it's got a lead coefficient. One way to do this is to split up that middle term into those two numbers we just found. And then what we actually are doing then is just turning into a situation where factoring by grouping will work. So if we factor by grouping now, common factor the first part, 5x, and we're left with x plus 2. Minus 2 can come out of those, and you're left with, well, x plus 2. and then that will give you x minus 1, 5x minus 2, x plus 2. You've got it all fully factored. So there is a look at the factor theorem and how to factor all sorts of polynomials. Find that factor by finding something with remainder 0. That's the key.